Hello, good morning, and welcome to this seminar from Lancaster University. It's the latest in a series on developments in materials science in conjunction with the European Regional Development Fund project, GISMO. GISMO is Greater Innovation for Smarter Materials Optimisation. And I'm James Stancombe, Project Manager for GISMO. We're pleased to be joined this morning by Dr. Julien Doucet, GISMO Innovation Fellow from the Materials Science Institute at Lancaster. And he is going to speak about post-polymerisation functionalisation and the opportunities it presents in new product development. Just before we hear from Julien, there are a few housekeeping points. The seminar is due to last for 1 hour. Please turn off your camera and mute your microphone beforehand. If you have any questions for Julien or comments on what you see and hear, please write them in the chat box and we'll collect them up and pose them to Julien at the end of his presentation. But that's enough on housekeeping. It's time for the main event. Over to you, Julien.
Right, thanks for the introduction, James. So this morning we're going to be trying to showcase how post-polymerisation functionalisation really embodies the future of polymers. First thing, I'd like to really hope that the presentation will be technical enough, not too technical. I will try to make it not too academic, and really really showcase all the opportunities that it offers. And I wanted to start this presentation just showing the public perception of polymers through what comes through the news. And really, polymers in the news is plastics, and mostly plastics waste, whether it's funding for plastic recycling, whether it's building of new plants for recycling, or pointing out what companies produce the most single-use waste plastic. This is really the main focus of the news. Of course, with the pandemic, we've had also some attraction for developing antiviral surfaces, which, I mean, those surfaces will always mostly going to be polymers. So that's this kind of other angle in the news. But really, the main focus is about plastics, and so that really brings me to the second sort of introductory slide that I wanted to present before getting into the main subject of the day, which is the dilemma that these plastics offer to polymer scientists. As you can see from the production since the 1950s, it's been ever growing, almost like exponentially, and it's been growing in volume and complexity. So we need more and more complex material, but at the same time, we're being more and more worried about the sustainability of these products. As you can see, the plastic production this time representing this tiny green sliver, which is basically renewable sourced polymers, biopolymers. So we can see it's a very small proportion. Really, this really shows the sort of dilemma that polymer chemistry is facing. We want more and more complex materials, but ideally we're trying to make that more sustainably. And hopefully this presentation on post-polymerisation functionalisation will exemplify a few cases on how this can be done. So just before getting onto the presentation, I really just wanted to put this slide to really pinpoint why your business might be interested in these areas. Well, if you're needing a polymer material with specific properties that is not currently available, post-polymerisation functionalisation will be an ideal platform to do that. If you're already producing polymers and you'd like to extend your catalog, well, that's another way where we can use very efficiently post-polymerisation functionalisation. And finally, and tying back to the sort of sustainability, if you want to valorize waste polymers, there should be some opportunities to do just so, and we'll see that in this next hour comment. Well, a brief outline. So we're just going to be going through some polymer functionalisation just to show really how it stands out from the strategies employed in post-polymerisation functionalisation. And we'll see what post-polymerisation functionalisation is. You might see most of the slides are, I've just called it PPF because it's a bit of a mouthful and it's a bit long on the slide, but I'll try to call it the full name every time. And so we'll just see a few slides of what it is and why it's powerful and how it can be used, and then a few methods that to implement post-polymerisation functionalization. And then we'll just diverge and go on to upcycling of plastic waste and methods that can be used for that, before finishing with some case studies that we've been working in our group at Lancaster University. First, I mean, it's been a lot of like sort of slides before getting onto the subject, but I thought I'd give you a bit of my background so that you get an idea where I'm coming from with this presentation. So I've had held a PhD in synthetic organic chemistry since 2014. Since then, I've had several postdoctoral experiences, catalysis, natural product, and more recently on post-polymerisation functionalization. And since last year, I've been an innovation fellow in GISMO at Lancaster University in the Sweeney Group, and I've been recently appointed lecturer in chemistry at Lancaster University. Really, what I try to show from this background is that I'm not a polymer chemist, which might sound a bit confusing, but actually what we're trying to do is we're trying to develop new method, taking inspiration from the small molecule chemistry, which has hundreds of methods, maybe thousands of methods to transform starting materials into products. And polymer chemistry and post-polymerization functionalization in particular is a lot more scarce in this area. I also like to pinpoint that at Lancaster University we have a really good pull for polymer chemistry. There's some work being done on sustainable polymers and on polymers for like used in the energy area, whether it's batteries and things like that. So if your areas are broadly in polymers, we might still be able to help you, even though it's not post-polymerization functionalization. All right, starting with now the bulk of the work. So just a little bit about polymer functionalization. This was first developed in the first part of the 19th century, and had a slow progress for about 100 years until basically the world of plastic started in the early 50s and 60s. That really contributed to the development of polymerization methods, and really now we've got a varied, much more varied ways to polymerize material, which tolerate a lot more functional group. That said, that still generally requires the design of specific monomers, which can take some time, and you're not guaranteed with the products you get. And there's a limited number of these monomers, so it's not ideal for example, the synthesis of polymer libraries. And the alternative that we're proposing is post-polymerization functionalization. We're going to see in the next slide how that differs from the traditional way of functionalizing polymers. So if we look at the polymerization reaction, let me just put my laser pointer. I might just put a little bit. So if we take a monomer here that's got a functional group in green, you do a polymerization reaction, you get a polymer. This is a homopolymer, for example, but you can get very many architectures, for example, random copolymers or block copolymers. I mean, there's many more types of architectures of polymers. And this is not the subject of this talk, but I'll just put a few there, that the kind of basic ones. If we compare that to post-polymerization functionalization, the idea is more, you take a base polymer and you pick some functional groups that you're interested in, and you try to attach them directly to the polymer. So you can imagine that if you want to put 100 functional groups, this is a lot faster of an approach, because you just react at the same time, the same starting material every time. So that should be faster, as long as you get methods that are working really well. Another bunch of architectures I could pinpoint. Again, it's not exhaustive, but you can get obviously brush polymers with one type of group or two types of groups here, and then you can get a functionation of the chain ends, whether you want to do block copolymers, star polymers. I mean, again, the opportunities are multiple in terms of architectures, and post-polymerization functionalization can surely achieve all of those. But the strategies then for post-polymerization functionalization really depend on the type of base polymer, and hopefully the scheme explained to you pretty well what I mean by this. So traditionally was done in post-polymerisation. Functionalization, you take a monomer that's got a small functional handle, not a very advanced functional group, but that would be tolerated in polymerization. You get your polymer that's got this small handle, and then this small handle will be reactive to a certain type of functional groups. So all you have to do is pick molecules that got that functional group on it, and then you can attach them very efficiently, like in quantitative fashion, onto your polymer. Again, this is known as a homopolymer, but this works just the same if you take a random copolymer. So that's one first approach. If you're interested in the other approach, which is taking a commodity polymer, in this case, you take a polymer that has no pre-functionalization. So it's a lot more difficult to achieve a quantitative. You're not going to get quantitative functionalization. You're going to struggle to perhaps direct where the functional groups are going to be introduced. But the advantage is that you can just take this one platform that's going to be cheap and widely available, and you can still introduce some functional groups onto them. And then obviously you can just screen the properties, and if you're happy with the properties, that's all that matters, really. To summarize those few slides, just puts a few aims and a few possibilities that we're going to see in the future slides that are possible. Really, the aim of post-polymerization functionalization is grafting small or large groups onto a base polymer. And the aim of that is to introduce biological properties, stimuli responsive functionalities. You can modify material surfaces, and you can fine-tune physical properties in all the ways that you can imagine. So let's just get onto a bunch of examples showcasing how this is done. I thought at first I would pick an historical example that everybody would know about, This is vulcanization of rubber. So if you could take, this was developed in the early 1800s by Goodyear, and basically was at first just a reaction of sulfur and rubber with heat. So you take your rubber polymer chains that are like loosely floating with each other, and you use a material that doesn't have a huge amount of strength, and the properties of the polymer were not satisfying. So they thought to try to modify it, and the idea with that was the vulcanization using sulfur, which introduced cross-linking to the polymers. You can see those little orange bridges, and these cross-linkings just really improved the strength and the properties of the polymer. If we look a bit more into the cross-linking, although I'm not going to detail all of those, and this is again not an exhaustive list, just wanted to pinpoint that you can see this double bond in here, and you can see that the cross-linking has happened next to the double bond. So that's again kind of an example of a primitive handle that was used for the functionalization to introduce those polysulfide linkages. And if we look at like how it looks like, you take this is the rubber and sulfur mixture, you put that on a hot plate, and then you get this sort of like charred color of polymer of the vulcanized rubber, and this is basically tires. So obviously this might seem a bit like a basic example. It's not very technological, but since the original method, just using sulfur, has been developed using a very advanced catalyst to control precisely the cross linkages you can get and control the properties of your tire. I mean, and if you think about, let's say, Formula One or MotoGP, and you think of like the tires used in there, you can definitely see how those are like high-end products that require very precise work on them. And again, I hope this relates to everyone, because really, it's not post-polymerization functionalization is not just used for things that are super advanced. It's used for things that might seem basic, but actually are quite complex as well. Just moving into now more, again, classic sort of high added value materials, which is in medicinal chemistry. We're going to see a few examples in there. This first example there is an example where the polymer was used as a drug delivery system. So in all those slides, I've tried to keep a little scheme like that with the little schematics that I've shown before, so that hopefully it helps to understand what's going on in the functionalization that we have. So in this case, we got a random copolymer which has got this functional handle here that was a double bond, and then attach those molecules that got sulfur on it very efficiently. And onto those molecules, they put a drug called cisplatin. There's an anti-cancer drug, and the result was that the polymers that they got provided a way more efficient delivery of the cisplatin drug, and that was manifested by a higher bioavailability of the drug. Another example that is very similar, again, it's another drug delivery example. In this case, with the first that the polymer chosen was like a simple homopolymer. I mean, it was not a commodity polymer, and so the polymer is polyglutamic acid, which is just the bottom part in here that has got those pending change with carboxylic acid groups on the end. But this is still a homopolymer that is simple to obtain, so it's still fairly common and simple. And in this case, they've attached this drug called paclitaxel, again another anti-cancer drug, and again, similar effect than previously, increased bioavailability and more efficient drug delivery in the body. And the advantage this time, again, also is that the polymer itself, polyglutamic acid, is biodegradable, so it's quite easily eliminated from the body, which is an advantage. A last example of is post-polymerisation, functionalisation using medicinal chemistry. And this time it's used for gene delivery. So, I mean, the polymers made don't include the sort of medical part that you're trying to give into the body. This time they are the actual medium in which the gene will be delivered. And really what this slide is more aiming at doing is showing that from one single homopolymer with a small epoxide handle there, they can easily get 3 polymers by reacting with 3 different types of reagents. But you can imagine that if you react this with 100 types of reagents, then you can make 100 types of polymers and screen their properties and choose the best one. So really this slide is more to highlight the fact that it's really easy to obtain a wide library very quickly using post-polymerisation functionalization. So now we're just moving into a different category of polymers, although some of those stimuli responsive polymers are also used in biomedical applications, but we won't go into just the end super end application, but just explain what they do and what stimuli they respond to. So classic stimuli are temperature, pH, light, chemicals. Really, those are the classic type of stimuli that those polymers that we're going to be talking about are responsive towards. So first example here is a homopolymer which has 2 handles at one on each hand of the polymer, and then just attached a stimuli responsive functionality. The stimuli responsive groups are those azobenzene moieties there, and these azobenzene moieties, when you shine light on them, you get isomerization of the double bond, which changes the properties of the polymer. How it manifested itself with the whole molecule here is that first thing, if you increase the temperature, your polymer was soluble, becomes insoluble, and then if you shine some light at it, it's soluble again. So that just shown like this, you might not really see a direct application, but those azobenzene polymers, basically what they do is harvesting light energy and then they release it as heat in the medium. And basically, there's examples of this trying to be incorporated in car windscreens, for example, so that you get anti-frost applications. Basically, it just releases enough energy so that your windscreen doesn't go below 0 degrees and stay unfrozen at night. So that's some examples in which it's been used. But again, the application for this can be way more advanced and tailored to what you want to do. This is just kind of a proof of example that things respond to light and temperature at the same time. Another example, this time is a polymer that is responsive to CO2 and heat. So this was a homopolymer functionalized with 2 different types of groups, which we can see here. One group is this one. One group is this and that, and then 2 examples I've done. One with the cyclopropylamine here and this long molecule here that's got a guanidine functionality at the end. And again, similar concept as previously. You take a polymer, It's soluble, you heat it up, then it becomes insoluble, and if you add CO2, it solubilizes again. And in this case, the most sort of obvious application is just the sensing the presence of CO2, because obviously you get a material that changes its appearance, whether there's CO2 or not. So you can use that as a sensor, and there's examples of that trying to be used for CO2 capture as well, which again, in the current race for sustainable pathways for science, this is a very interesting approach. Now, moving from the stimuli responsive polymers, I just want to show one example of surface functionalization. So in this case, this group in 2008, they just picked polymethyl methacrylate, which this time is very common polymer, and functionalized it with some groups along the chain randomly. For this, they use this photocatalyzed nitrine insertion. I'm not going to go into the chemistry detail, but basically they attach these functional groups onto the side chains of the polymers. These groups, they have got like another group that has not been drawn on here, but that has got functionalities that can allow you to bind some proteins. So what they did is they bound the protein onto this, and then they wanted to prove that that actually they had worked. So what they did is they took their bit of plastic, they masked some areas so that there would be no reaction in those areas. Then they went all the way through what I just presented, which is functionalizing and attaching the protein. And on top of that, they added a dye that would bind, that is known to bind to the protein. And then there's just some UV light at it, and you can see the green fluorescence here. So that just was the proof that the functionalization had works. And then the use they described for that kind of device is what they like to call lab on chip applications. So if you can imagine an array of, like, let's say 100 of those chips that have got 100 different proteins that can selectively bind to 100 different pathogens. And if you imagine you're in the middle of like in the middle of nowhere in a very remote area, and you want to like test the water or like another medium that you don't know why it's gone in, and you want to see what it has. So you just take your natural medium, like let's say water, pour it onto your array, and then if you can just shine a light and identify which proteins have been binding to a pathogen, you can identify the pathogen, and it's a very quick way to analyze something. So these are the kind of applications that you can have that again are very powerful. And finally, in terms of like the sort of examples, I just want to depict one where it's just simply that the properties of the polymers that have changed and that were used for a different application again. In this case, that group published that work in 2016. They picked a tri-block copolymer, which has on one of the blocks has got one handle, which is that alkyl chloride here. They reacted that with a phosphine and got this functionalized ionic polymers. And those ionic polymers can be used for anion transport. And they've proven that they can use this as a membrane. And through that polymeric membrane, some anions are going to cross. And this is very useful, for example, in fuel cells, which again ties really well with sort of sustainable energy, and it can also be used in water purification, for example, which again, in a world where water resources are getting lower, this is very important. So again, I hope this really showcased the power of what can be achieved. And I want to say endless opportunities in terms of the applications. Anything can be thought of. I don't think there's anything too stupid or too complex. I mean, things that are very complex will always take a lot of time to achieve, but because there's a wide variety of polymer architectures, we can do a really wide number of applications. And really, the bottleneck of this is the number of methods to attach the functional groups onto the polymers. Like once the polymers are there, you can see that the variety of applications is quite wide, but attaching those can be quite difficult. And I'm just going to show you a bunch of methods that are widely used. briefly. So most of these methods that are widely used are methods that give you really quantitative functionalization, and they've been coined click reactions. I mean, that name was actually given by Barry Sharpless, who is a Nobel Prize laureate, and he called these reactions click reactions, and that was actually on sort of some small molecule chemistry. Again, highlighting the fact that taking inspiration from the small molecule world and putting that into polymer science, you can really achieve a lot of things. And the basic precepts of that are that you don't want to need an excess of any of the coupling partners. You want the reaction to work large scale. You want the reactions to be fast, to give you a high yield, stable compounds, and really be like tolerant of reaction medium and functional groups that are present. That's really what matters in those reactions. And a small non-exhaustive list of those reactions are the first two reactions are like reactions of activated esters, where the esters are so reactive that you react them with like amines, simple amines or hydroxyls or alcohols, and they just react and give you the amides and esters. A third possibility is this copper catalyzed azide alkyne click reactions, cycloadditions. These are actually the ones that gave the name that Sharpless gave the name click reactions for. There's a bunch of thiol-mediated chemistries, which again originated mostly in protein coupling, but now this has been adapted to polymer modification as well. And there's a bunch of other reactions that can be all descriptions of click reactions. They're just not as used, perhaps because they're not as known, or the scope is not quite as wide. The scope of reagents that can be used for them and a bit more complex. Just to like briefly show, I thought the scheme picked from that publication was really exemplifying what we mean by click reaction. The click reaction is as simple as putting two Legos together. That's really what you're aiming for when you're talking about click reaction. You just put it in together in a flask, and the two coupling partners are assembled. That's really what matters. But trying to move from those click reactions, as I was saying, there's many other ones, but more importantly, I think it's important to take some inspiration from the small molecule literature, and that's also what we're trying to do in our research group. And I thought this example was very interesting. So this is an example of a transition metal catalyzed and photoredox catalyzed reaction. So photoredox catalysis is literally been developed since 2008 for organic molecules, and so you can see it's a very new field compared to like the age of science of chemistry. Sorry, and despite the fact that it's only like just above 10 years old, for small molecules it's been almost fully screened out and scoped out. I mean, everything is everything that can, not everything can be done, but most things that can be done have been discovered, and you can do a lot of things with these things. And it's very interesting to see. There's already some example in the polymer literature, just reacting this thiol, coupling it, reacting with those alkene double bonds there, and getting a very efficient coupling. Again, in this case, the molecules they get is not so much. I'm not showing this so much for the application of those molecules, just to show that if you take inspiration from new things coming from the small molecule literature, you can just works fine in polymer science, but just have to try it first. If you don't try it, you don't actually get it. And really, what this is bringing us to is commodity polymers, because all those click reactions, they always require that Lego block being there on the molecule before being able to do the very efficient coupling. And the thing with commodity polymers, they have none of those handles to do the coupling efficiently, and that's been really the reason why commodity polymers haven't been used as much in post-polymerisation functionalization, and it's a bit of a shame. If I just put this this graph, so this graph is only the waste plastic generation every year since the 1950s, and you can see it's 300 million tons. I mean, so we can fairly safely say that there's quite a lot of material that could be used and that it just ends up in landfill. Of course, some of this is being recycled, but not a lot. Not a lot is being recycled. So that really gives a lot of potential for the valorization of those wastes. And a way to do that is, of course, because those are already polymers, is post-polymerisation functionalization. So if we just go, sorry, a little bit more, to go a little bit more in detail about the recycling of plastics, the traditional method, you take plastics, you sort them per type, and you remelt them back into their original shape. And that works only to some extent, because there's you are increasing the number of impurities by doing that, and the quality gets lower every time. And an alternative method to that is to try to make products which have higher value than the original plastic. And that's been coined up as upcycling. And generally, there's two ideas in this field. It's either you take the polymers and you depolymerize them, as in you form back the building blocks that these polymers were made with, and you can use those building blocks for more polymerization reactions or for other applications. And the alternative that actually interests us is post-polymerisation functionalization, which is what we're going to be talking about in the next few slides. I just picked a few methods that have been developed to do this on commodity polymers. A very powerful work here, published in 2018 by the Leap Fast groups. In this case, I take basically, I think they're mostly polyolefins blends, but they don't have to be. They can be polypropylene. And what they do is, under photocatalyzed conditions, they attach this xanthate group there. And this xanthate group, so I should have color-coded the scheme. This xanthate group is basically the functional handle. I mean, that group, just as it is, it's not really particularly interested, except you can react that group to do much more chemistry and get a functionalized polymer, which they've shown. They did some functionalization, they did some cross-linking reactions, and they also grafted other types of polymers onto it. So that shows really the power of the method. And the main point that were pinpointed in the paper is that there's no chain scission. So what I mean by chain scission is basically when the polymer is getting chopped off in multiple bits during the functionalization process. And with commodity polymers, because there's no handle, you have to use harsher conditions generally to achieve functionalization, and generally it just breaks down the polymer to something smaller, which can still be, you can still use the product potentially, but it can complexify the purification, and you can't always guarantee where you're going to end up in terms of property, because the molecular weights of the polymer change too much. So that was really the main thing of this reaction, is that it was mild, and they could achieve that without breaking down the polymer. And on top of that, they install a handle where you can do several types of functionalization there. So then you can imagine synthesizing polymer libraries. If that R2 group there is very varied, you can imagine you can do like 100 types of polymers, screen the properties afterwards, and pick the one you need. Another example that is very similar, again, it's literally pretty much the same, except the handle is different. So this time it's rhodium catalyzed process using polypropylene, and they just end up with these alkyl boronates there. And at the time, all they did is oxidize them with hydrogen peroxide, and they got those hydroxylated polypropylene. So again, you can think, if you think about the polarity of polypropylene, it's just carbon and hydrogen, so it's really apolar. It's going to be hydrophobic. If you manage to install a ton of like polar groups on it, or on the surface of it, if you could do that just on the surface, you could imagine turning like your basic plastic into something that is hydrophilic. So that could have all sorts of applications, and that can be interesting. I'd like to add on top of that since that report published in 2005, since then, many reactions from the small molecule chemistry world managed to react those alkyl boronates. Back then, they were not so reactive, but these days, there's many possibilities of reaction that we can do with them, and really we could just install like many different functional groups, not just hydroxyl. So that again is another advantage. Just following the literature, the development again of small molecule literature gives you more opportunities as time progresses. A final example of use of commodity polymers is this time the transesterification of this methyl polyacrylate polymer. They just use a catalyst to activate this ester group and react it with various alcohols, and they get process esterification. And you can imagine that, again, if this R group possesses any of the functionalities that are presented in the first part of that seminar, you can end up with a stimuli responsive polymer or drug delivery systems. Any of these really is possible. So that's really the power of this functionalization. Again, just taking like standard polymers. Another another area that is not quite a commodity polymer, but is still kind of upcycling, is naturally occurring polymers. So there's many of these present in nature. I mean, the most basic one that everybody should be aware of is carbohydrates that we consume every day. Those are generally some polymers, but this is not really the one that we want to try to modify. The ones that are generally used for waste valorization is lignin and lignocellulosic waste. So those are basically the waste for the paper industry. So again, you can imagine there's quite large quantities of that. And then the other area that has been quite highly valorized is chitin and chitosan, which is basically the waste from the shellfish industry. And I just wanted to pick one example, highlighting that. Again, I could have picked like hundreds probably. It's been one example where they take chitosan there and they functionalize this primary hydroxyl and this secondary amine. They can do that selectively, do either or, and then they say you can use that for many biomedical and industrial applications. But you can imagine again that if you can attach a whole sort of variety of groups on there, you can introduce those stimuli responsive properties or attach a drug to it, or all sorts of possibilities really. And this really brings us now to kind of the last section of this presentation. I realized that I might have been talking a bit too fast, but I hope it was okay. And this last section is presenting some of the work that we have done with companies at Lancaster University. So I just wanted to pin those two companies. The first bit of work was done with Infinium. In this case, they wanted us to introduce some functional groups onto a polyisoprene-based polymer. I can't present to you exactly the actual groups they wanted on top of that because this was all done under non-disclosure agreements. But I'll just put a very general scheme down there. And basically what they had done is they've done some computational studies to identify some target molecules which they were interested in. And they said, well, can you just put those molecules and use that alkene handle as in order to functionalize them? When you look at the literature, again, there's really no evidence solution. There's nothing obvious in the polymer literature to directly attach the functional groups. They were interested to that double bond there. So we went back to looking, again, small molecule literature. You'll see the running sort of theme. And even in small molecule literature, this is a difficult functionalization. I mean, a tri-substituted double bond, this is very hindered, more so even in the polymer architecture. Luckily, in the past sort of 5 to 8 years, there's been the development of many hydrogen atom functionalization. So generally, those are very good to functionalize double bonds. And there's been some methods using iron, which again is a sustainable metal. So it's even more interesting if we can do post-polymerisation functionalization using kind of widely available metals that are non-toxic. I mean, it's even more interesting. And we've just adapted that to the functionalization of this polyisoprene based polymer, and we got the 4 examples that they wanted, and we obtained up to 60% functionalization of the double bond, which was significantly more than they expected that could be possible. And those are just being screened in the area that they're doing. Another case, another example we work with, this is quite significantly different, but you can see how more could have been done if it had been the project. It's work done with Kerax. So Kerax is a local company, and they try to valorize the residues obtained from pyrolysis of plastic. And those waxes are generally quite nasty looking. They're like pretty smelly, and the color is pretty dark. So they wanted to refine the quality of those waxes, just removing the impurities that make them smell and be colored, which was achieved. But more so than just the process of doing that, what was working on those polymers and analyzing them, we realized there was again a double bond functionality, and now you can see how similar that looks to the previous slide I was showing to you. So you can imagine all those things that we did previously, we could have done them also with this, for example, this waste wax. So again, it could be a way to valorize things. I mean, whether the polymer architecture would have the right properties is another story, but you can imagine that many possibilities are possible based on this example. What was done here was first the oil fraction of this wax was extracted. So wax is always a mixture of like more hard parts that are like the solids and an oil, and then just form like a waxy texture. So the oil part was extracted, and that actually contained most of the color, and the leftover wax that I didn't show here was pretty colorless. And then this wax was simply hydrogenated, and we ended up with this colorless solid there, waxy solid there. So again, it shows that we've obtained, we managed to modify the properties by simply a simple reaction. I mean, in this case, we haven't really added functionality because we just removed the double bond. So if anything, we've removed functionality, but you can imagine, and I can reassure you in the fact that obviously, at least the previous method that I showed in the previous slide, we definitely worked with functionalize this, and you can do simple reactions like hydroborations. You can get alcohol groups on there. You could use that as transesterification material, and because the molecular weights of these waxes are like in the sort of 500 to 2000, it wouldn't necessarily modify a lot the molecular weights of some like higher molecular weights polymers that have got groups in which you could do some transesterification. If you think, for example, that PMMA, polymethyl methacrylate example before, if you end up putting an hydroxyl chain on this, you could use this as a nucleophile, and you could incorporate that into a new polymer. So basically, you could directly like attach, not just incorporate in polymer media. You could attach some waste. So that's I hope this shows how the power of the post-polymerisation approaches, and now you can really use that for upcycling of waste, which is of course something very important in the search for sustainability. So as a conclusion, I hope that I managed to demonstrate to you that there's a bright future for post-polymerisation functionalization with like limitless opportunities, I want to say. I mean, really, the type of application doesn't really seem, well, it's only really hindered, as I pinpointed before, by the methods for which we need to expand on to be able to very precisely functionalize things. I mean, the dream word for, let's say, drug delivery is you take this polymer carrier there, and on the polymer you attach, let's say, two types of drugs that you want to deliver into the body. You attach some bits that you can do some imaging on. So once they're in the body, you can do imaging, like the traditional medical imaging possibilities. You also attach a targeting bit. So basically this bit will be selectively binding to receptors in the body where we know the disease needs to be treated. And so basically you give that to the patient. This targeting moiety gets to the selected site in the body. Then you can imagine some stimuli responsive linkers with those drugs. So you can, let's say, shine some light, and you can deliver the drugs the way you decide it, at the pace that you decide. And then you can do some imaging afterwards or during to see if actually the polymer carrying all the drugs has been delivered to the right places in the body. So this is really the dream world of medicinal chemistry, but we're not super far off this. I mean, there's probably only maybe one or two things attached to the polymer, not like 5. But you can imagine where I'm going with this. And another area is really expanding the possibilities on plastic waste valorization. So I've shown you a few methods. There's many more methods that work pretty well when you just take your like lab sort of like clean, brand new lab conditioned plastic. So you just buy some plastic of that type, you functionalize that, works really well. But doing that on waste where there's potentially mixtures and there's lots of additives in plastics, that can present some extra complications. And really the ideal case is you take a mixture of plastics, you react them, and the only the types of plastics that are reactive with your reaction reacts, and you can extract those out of the media and use those for added value products. And then you do a different types of reaction with whatever your leftover, which will be targeting a different type of plastic. In this way, you could just imagine like a massive vat of like ground plastic, which you just react and extract things sequentially to valorize products. So you could, that's really the idea there, and this would be incorporated in like the what is called circular polymer economy, and really we could contribute significantly on the increased sustainability of polymeric materials. Well, that'll be all from me. I hope you have enjoyed, and let me know if you have any questions.
Okay, Julian, thank you so much. That's a very comprehensive run through of the topic, and my scientific education continues. Not only have I added Langmuir Blodgett to my lexicon now on the back of coatings, but I now know about equimolarity, albeit that I may only be able to use it ever in a Scrabble game. But if you have any questions for Julien, now is the time to ask them. And if you'd like to put them into the chat to do so, that would be great. And we have a question for you from Noah. And Noah says, what would you say is the main advantage of post-polymerisation functionalisation compared to the standard way of synthesizing functionalized polymers?
Thanks, Noah. That's a very good question, really, because it really drives the essence of the area. I would say the main thing to get out from this is that if you need to screen 100 polymers to find the best property, this is really offering you this. So you can synthesize polymer libraries super quickly, especially in those cases where you have a click reaction, where we know that you'll be able to attach the things without any problems, and you can do 100 different types of click. Well, you can do with the same type of click reaction, you can choose 100 different coupling partners and get 100 polymers. And ideally, this is what we're trying to develop also for more common plastics. And if you could do that with common plastics, then that would really increase the scope of it. But synthesis of polymer libraries, I would say, is the main answer.
Okay, thank you very much for that. Any other questions for Julien now? Well, do you know what? It looks like you got away lightly there.
Yeah, it looks like it. Well, if you have any questions that you can't think of now, but that you got some that you want to ask in the future, just don't hesitate to contact us. James can give you some more details maybe on the website. But I mean, if you already joined the seminar, it means you found the website. So yeah, just don't hesitate to drop us an email about anything regarding this topic.
Yeah, I think it's important to point out that we've recorded the seminar, so you'll be able to watch and listen to it again, and we'll be sending you the link to that later on. Okie dokie, thanks, Julien. Well, I'll just finish off matters and just to sort of let you know, really, that if what Julien's talked about today is of interest to you, it may well be that the GISMO project can help you. And there are a number of ways that we can do that. our sort of entry offer, if you like, to any business is that we gladly put your materials to the test in what we describe loosely as a materials MOT. So yes, we'll test your product. We'll give you advisories just like you would in a normal MOT. How much tread you've got left on your tyres, as it were. But we'll go a little bit further than a standard MOT. Not only will we test and tell you what the position is, situation is with your materials, we'll go one step further and we'll help you to either put things right or to improve them in the way that you'd like. And there are a number of ways in which we can do that and try to describe them here. So we can look at things like the antiviral and antimicrobial resistance that your materials offer through our virologists here at Lancaster University. We can look at how that they can be protected through coatings potentially. And if your product has a coating, we can look at the characteristics and effectiveness of it. In fact, we can put your materials under the microscope literally to look at their properties and performance, their strengths and limitations and the like. And if, as Julien has described today, you may be looking for perhaps new or alternative materials or to improve their your environmental sustainability, whether that's through the waste, recycling, upcycling, and as we've heard this morning, through downcycling too, then come to GISMO and we'll have a look at that for you. And if you just like to sort of have a look at your products and materials and think, well, how can I introduce smart properties into them? Our scientists are there ready and waiting to help you to do that. If you have a product which perhaps would benefit from some kind of physical prototype through 3D printing or virtual prototyping, we can help you with that. Or if you simply want to benchmark your the performance of your product against another, we'll jump on it, we'll stamp on it, we'll stretch it, we'll heat it up, we'll take it down to some of the lowest temperatures imaginable, we'll break it, we'll do anything to it that will give you a set of performance notes where you can compare your product against another. If any of that or all of that is of interest to you, do please get in touch. And here's the way that you can do that. If you'd like more information on the project as a whole and the capabilities that Lancaster has got in materials to support you, do take a look at our website, smarter-materials.co.uk, and hook up with us on social media, both in Twitter and LinkedIn. As I said before, this seminar is being recorded and you'll be able to watch it later on our YouTube channel, where you can also see other seminars that we've held over the last 6 or 9 months and pick up on those as well. And if you'd like to get in touch, if you have any more questions with Julien, if you'd like us to potentially help you, do email us at gizmo@lancaster.ac.uk or give us a call on that telephone number there. Give me 5 minutes to get back to the phone before I get the chance to answer it. But that apart, that's pretty much it for this morning. We'd like to thank you for taking part, for your attention this morning, and hope you have the rest of a good day. Thanks so much, and good morning.
No, thank you, everyone. Bye.